Alrighty, in this video we are looking at geometric sequences. Our objectives for this section are to determine whether a sequence is geometric, explicit and recursive formulas for geometric sequences, and to determine a given number of geometric means. So let's get started. I want to present to you the idea of a geometric sequence. When you have one, the ratio of any two consecutive integers is going to be a constant, and that is called the common ratio. And so you'll notice the larger term over the smaller term, or I should say the like second over the first or the third over the second is going to give you that common ratio of R. So let's take a look at both A and B here and determine if they are geometric. If it is, we're going to give the common ratio. To do this, I want to look at each of these terms and look at them in pairs. So looking at the first two, it would be 3 over 1, which is 3. The next ratio would be 5 over 3, and then it would be 7 over 5. Now those are all different ratios, so this is not geometric. But let's look at problem B now. We're looking at 2, 3, 9 over 2, and 27 over 4. So you're going to have to do some division of fractions here and make sure that you maybe take out some scratch paper and check this yourself. The first ratio would be 3 over 2. Then you would have 9 over 2 divided by 3. Well, you'd have to multiply by 3 by the reciprocal, so you'd have 9 over 2 times 1/3, which is 3/2 again. And then it would be 27 over 4 divided by 9 over 2, but again, instead of dividing by a fraction, multiply by the reciprocal. So 27 divided by 4 multiplied by 2 over 9, and when you simplify, that does give you 3/2. So each time here we have the same rate, and this is going to be geometric because of it, and that rate is 3/2. The recursive formula for a geometric sequence is just going to be the rate times the previous term, and you have to know your first term. Very similar to what we've seen before with recursive formulas. So I want to talk a little bit about, I want to work through this so that you can actually discover the explicit formula. And we're going to look at the pattern here. Let me show you what I mean. Let's look at the second term. The second term, if it was geometric, would be the first term times the rate. That makes sense, right? According to the formula that we just saw, that recursive formula. The third term would be the second term times the rate. But let me remind you, the second term is the first term times the rate. So I've substituted in what the second term is equivalent to. And now using some exponent properties, r times r is r squared. So really, A3 could be represented A1 r squared. Tracking with me so far? Let's look at A4. A4 is A3 times the rate. That's using the recursive formula. The previous term times the rate. So in this case, it would be the third term times the rate. But we just saw that the third term is really the first term times r squared. Now r squared times r is actually r cubed. So we've rewritten this. A5 is, well, the fourth term, the previous term, times the rate, but we know that the fourth term was actually the first term times the rate cubed. I'm just substituting in what we just found. And now look what we have. We have r3 times r, which gives us r to the fourth. So what are we noticing here? For the third term, it was the first term times r squared. For the fourth term, it was the first times r cubed. For the fifth term, it was the first times r to the fourth. Why don't you try and determine what it would be for any term? Try in terms of n. Pause this video and do that right now. All right, so here's what we can say. We know that a sub n, the nth term, is the previous to n times r. But that's really going to be 2 previous times a1 times that rate yet again. So if you wrote that an is a1 times r to the n minus 1, you are correct. And this, ladies and gentlemen, leads us into our explicit formula. Our explicit formula for geometric sequences is the first term times the rate to the n minus 1 power. This is the explicit formula because it is just in terms of its position. And you also have to know a1 here to be able to determine any questioned term. So why don't we look at this example? We're going to write both a recursive and an explicit formula for this sequence. It is geometric, and it's the sequence 4, 2, 1, and it continues on. So to be able to do this, we need to first know what our common ratio is. And that would be the second term minus the first term. That's 2 over 4, which simplifies to 1/2. So that is our common ratio. Now, with that, we're going to plug that into our recursive formula. Our recursive formula, it would be a sub n is equal to the rate, which was 1/2, times the previous term, and we have to include what our first term was. Our first term was 4. Okay, last part, let's give an explicit formula. We're going to substitute in our given information into that formula. It would be 4 times 1/2 to the n minus 1. You could separate this, the exponent. Remember, if you have exponents, you can separate those as long as they have the same base. And if you take 1/2 to the negative 1 power, to get rid of that negative, you have to switch it. And so it would be actually 2. 1/2 to the negative 1 power is actually 2. You can pause this video and check that right now in your calculator. And we can simplify this even a little bit further and write 8, because 4 times 2 is 8. Now, I won't ask you to do this every time. I just wanted to kind of show you how you could simplify that. So if you're asked to give a simplified explicit formula, this is it. If they just ask for the explicit formula, you can leave it where we started. Okay? So, what happens if you don't know the first term? What if you just know a random term in the sequence? That's where the generalized explicit formula is fantastic, because what we'll do is, instead of the position of 1, we will have the k position. So what we have here, an, which is the term, any term, a sub n, is equal to a sub k, k being the position, r to the n minus k. So those k's have to match. Let me show you in this example. We're going to write a simplified explicit formula for this geometric sequence, and we know two terms in the sequence. What we don't know is the rate. That's what we're going to be trying to find. So we'll substitute in. We're looking at, you'll want the larger term to be what you're setting it equal to. So that's a sub 5 is equal to a sub 3 times r to the 5 minus 3. That would be 28 when I substitute in equals 7r squared, because 5 minus 3 is 2. Divide each side by 7, and that gives you 4 equals r squared. And you would have to take the square root of each side, or think, just kind of common sense, what squared gives you 4? Now, I say common sense, but it's not always so obvious. It's both 2 and negative 2. So there are two options here for your rate, which means you're going to have two sets of answers, because there are possibilities here with geometric sequences. So let's substitute r in to our formula now. And I'm selecting my k value as that position 3. So a(n) would be 7, rate of 2 to the n minus 3. Or I could have a(n) equals 7, a rate of negative 2 to the n minus 3. And we're just going to leave that there.